Okay, I think my screen is visible to you.
Yes.
Yeah, so we'll start the lesson. So yesterday we will discuss about the interaction of matter with radiation. Okay, so that radiation is interact with matter in two different ways. So first one is the absorption, second one is the emission. Okay, in that so that absorption process we will also call it as stimulated absorption. Okay, generally simply we will call it as absorption or stimulated absorption. Why we will call it as stimulated absorption? This absorption process we will call it as stimulated absorption. What is the reason for that? Because we are using external source of light. That means we are using external source of light to send the electron from ground state to excited state. So that's why, so this absorption process we will also call it as stimulated absorption. Now coming to the spontaneous emission. Spontaneous emission is nothing but here emission process will occur. Emission means so the electron will jump from higher energy state to lower energy state. The electron fall down from higher energy state to lower energy state here in this process. So this process is occurs naturally. That means without giving any external source. Without giving any external source after completion of the lifetime of the electron in excited state, it will comes to the ground state. That emission we will call it as spontaneous emission. Okay, here lifetime of the electron is approximately 10 to the power of minus 8 seconds. Okay, so this is spontaneous emission. Now coming to the, yeah, so in that spontaneous emission photon will be emitted. So that photon energy is equal to the energy gap between the excited level and ground state. That means E2 minus E1. Now coming to the stimulated emission. So in that stimulated emission process we are giving in some external energy. Okay, so because of that external photon, what happened, these excited electron comes to the ground state, because of the stimulation. Electron coming here ground state. Okay, so this emission process we will call it as stimulated emission. See here, so because of that stimulation here, so two electrons is coming out, two electrons are two photons are coming out. Okay, coming to the, so this also same what I said, so there are some uh, properties are there, for stimulated photon, sorry, emitted photons in case of stimulated emission. Okay, what are the those properties means, so those photons, so that our released photons in a stimulated emission is in phase with the incident photon. So whatever the phase of the incident photon will be there, that emitted photon also having same phase and same wavelength as the incident photon. And the third one, travel in the same direction as the incident photon. Okay, so these are the, so some properties of the emitted photons. Okay, now we will discuss about the comparison between the spontaneous emission and stimulated emission. Okay, in case of spontaneous emission, that emitted light is polychromatic radiation. Okay, so that in case of spontaneous emission, that is a polychromatic radiation. Polychromatic is nothing but, so multicolor radiation will emit. Okay, so multicolor is nothing but, suppose if you will take led will emit single color only, but in that single color, so bandwidth of that color is very high. That means we will not get a particular accurate color. So suppose if you will take in middle, that color thickness is very high, so above, so it will color thickness decreases, below color thickness will decreases. That means, so there is a bandwidth of the wavelength or frequency is high. in case of polychromatic radiation. But if you will take monochromatic radiation, so monochromatic radiation means exactly single color. It will emit a exactly single wavelength. Single wavelength. So that means bandwidth is very less here. Bandwidth of the wavelength will be very less. I will tell you what is the bandwidth also after completion of this topic. Okay, this comparison I will tell you what is the bandwidth also. Okay, now it has less intensity. Okay, in case of spontaneous emission, that emitted light have less intensity. In case of stimulated emission, that emitted light has high intensity. So already you know that what is the reason for intensity? Number of photons per unit area. Okay, in case of spontaneous emission, what happened? Different photons will move to the different directions. That's why, so all photon will not come in a single direction. So that's why what happened here, intensity will be very less in case of spontaneous emission. Similarly, now coming to the stimulated emission, all photons are coming in a single direction. That's why all photons are concentrated at a particular area. So intensity will be increases here. Intensity of light will be increases in case of stimulated emission. Now coming to the spontaneous emission, in that it has less directionality and more angular spread during the propagation. Okay, so its directionality is very less. So I will tell the difference. So what is the directionality? So that equation also I will tell in properties. Okay, so here directionality is very less. Directionality is very less and more angular spread during the propagation. During the propagation. Okay, so now what is the how it will be angular spread is more means, see here. Now if you will take normal light here, so if normal light is started on here, so it will be spread like this, so that angular spread is very high. Okay, but if you will take laser light, here, so one photon is coming like this, another photon also coming same direction, that angular spread is very less here. Angular spread is very less. So this in case of normal light, angular spread is increases with the velocity of light. Suppose so if light is traveling at a distance, so 1 kilometer distance, so angular spread also same, it spread also 1 kilometer. Okay, so that's why in case of normal light, angular spread is, so that means its angular spread is very high. In case of normal laser light, angular spread is very small. Okay, now coming to the okay, so next point, what is that? It is a spatially and temporally incoherent radiation. So I will explain you what is the spatial cohesion and what is the spatial coherent and what is the temporal coherent. I will explain you. So in the properties, so here spatial coherent and temporal coherent, temporally incoherent. Spatially and temporally incoherent. So in case of laser, it will be spatially and temporally coherent. So that radiation is spatially and temporally coherent radiation. Okay, so now if you will take in this emission, light is not amplified. Okay, so if you will take laser action, stimulated emission, light is amplified. So we'll discuss how light is amplified. Okay, in that different we will discuss about the different types of lasers, CO2 laser, so many lasers we will discuss. In that laser, how by using optical resonator, here will amplify the light signals. In case of stimulated emission process. Okay, so we'll discuss in the how it will works, that amplification process, how it will work. So we'll discuss in that. So types of lasers. Okay, next spontaneous emission takes place when excited atoms make transition to lower energy level mm, voluntarily without any external stimulation. Okay, so that means in this process, in this spontaneous emission process, so spontaneous emission process, the electron will come automatically from excited state to ground state. Ground state. We no need to give any external stimulation. No need to give any external stimulation in case of spontaneous emission. But in case of stimulated emission takes place when photon energy equal to the stimulates an excited atom to make transition to lower energy level. Okay, so what happened here? So by using external source, by using external photon here, we are stimulating the electrons. That's why all electrons comes to the ground state at a time. See here, so suppose two electrons will be there here. So if you stimulate, so here two electrons will be there. If you stimulate with some photon here, that photon energy also, so same energy of the here, what is the band gap energy? Okay, so that's why, so what happened, so this photon is stimulated to the these two electrons. Now what happened, so three photons will emit at a time. So see here, three photons will emit at a time, so those are all are moving with a same direction. Okay, so like that same direction they will move, and phase difference also same, and frequency also same. Okay, in case of stimulated emission. Now coming to the
Sir, your PPT is not visible, sir.
PPT is not visible.
Yes.
So
It's
my
visible,
voice is
sir.
audible.
It's visible, sir.
Okay, yeah. Okay, visible right now.
Yes,
Okay,
sir.
Yes.
yeah. Okay. Now going to the next point. In a single downward transition, spontaneous emission results in the emission of one photon. Okay, so now if you observe the, so in case of spontaneous emission, we are not using any external photon. So that's why if one electron is so coming from upward direction to downward direction, so what happened? So higher energy state to lower energy state, only one photon will emit. So due to one electron here, only one photon will be emitted. Okay, in case of stimulated emission. Okay, while coming to the downward direction, we are using here external source of light. So that's why here, along with the, that means due to the electron coming from higher energy state to lower energy state, one photon will be emitted, and so we'll use one external photon to stimulate that. So that's why here, so two photons will be emitted. That means two photons will be emitting a so single transition. Okay, so this is, so that's why what happened here, intensity will be very high. In case of stimulated emission, intensity will be very high. Next, examples. So examples of spontaneous emission. So examples of, if you will take bulbs and LED, and so the sodium bulbs also. Sodium bulbs actually have single wavelength, but those are not spontaneous emission. Okay, that also stimulated emission only. So if you will take argon bulbs, sodium bulbs, so those all are the single wavelength bulbs only, monochromatic only. But so those all are spontaneous emission. Even LED also monochromatic, but that emission is spontaneous emission. But that emission is spontaneous emission. Okay, now coming to the stimulated emission. Stimulated emission is, in that examples, what is the examples of stimulated emission means? Laser is the so best example for stimulated emission process. Now coming to the characteristics of laser. Characteristics of laser here. So first characteristic, so high monochromaticity. High monochromaticity. So second one is high degree of coherence. High degree of coherence. So, and third property is high directionality, and fourth property is high brightness. Okay, these are the main properties of the laser. So compared to the ordinary light, compared to the ordinary light, so these are the major characteristics of the laser light. Laser light. Okay, so first one is high monochromaticity. So compared to normal light, if you will take any normal lights, so suppose already I said that, so sodium light is monochromatic. Sodium light is monochromatic. But so compared to sodium light, if you will take laser, so this is high monochromaticity. High monochromaticity. Okay, so why it will be high monochromaticity, I will explain you. See here, laser light is monochromatic or very pure in color. The bandwidth of the laser beam is narrow, while ordinary light spreads over a wide range of frequencies. The photons emit in the stimulated emission have same frequency or wavelength. Okay, so according to first point, so what is that first point here? So this is high monochromatic, okay, are pure in color, pure in color. So compared to the normal light, suppose if you will take, so one best example of normal light is sodium. Normal monochromatic light is sodium. In that, so bandwidth, how it will be, bandwidth will be there, I will explain you. So in x-axis, so we are taking here, so either frequency or wavelength, frequency or wavelength. In y-axis, intensity, if you will take intensity of the light, intensity of the light. So if you draw the graph between, that means if you will take sodium light, that intensity will be like this. Okay, so bandwidth, what is the bandwidth, means the range of frequency or range of wavelength. Okay, so in case of, if you will take sodium light, that will emit the orange color, orange color. So that wavelength is 598 angstroms, 598 angstroms. So at middle it have 598 angstroms, at middle it have 598 angstroms. But so that means at high intensity peak it's have 598 angstroms. So it's around that high intensity peak, there is a, so spread will be there, there is a spread of remaining wavelength will be there. So that is the how much it will be spread, how much wavelength it will be spread, that is called as bandwidth. Okay, in this band, so total radiation will be emitted in this range of band, in this range of bandwidth. Okay, so that's why it is not a purely monochromatic, it will not a, so that means it is a like orange color only, but it will not pure orange color. Okay, so it will be at middle high intensity, so high thick orange color will be there. So if you go to the, if you go to the so that means other directions, what happened, so that intensity will be decreases, intensity will be decreases. So that that's why it's not a pure monochromatic, pure monochromatic. So bandwidth also very high in case of ordinary monochromatic lights. Okay, now if you will take, yeah, if you will take laser light, if you will take, see here, 1 minute, eraser. Yeah, so if you will take in case of laser light, in case of laser light, how it will be monochromatic, we will discuss about what is the bandwidth also, we will discuss here. See here, if you will take laser light, so that laser light intensity peak will be very sharp, very sharp. Okay, so more than like this also. So this now bandwidth, what is the bandwidth here? So in between like this. So if you will take here, so approximately 10 angstroms only maximum. So what is the bandwidth in terms of wavelength? If it will be only 10 angstroms, so 10 angstroms bandwidth will be present. So distance between these 2 points is just 10 angstroms. That means this is very sharp peak, very sharp peak compared to the, so ordinary monochromatic light. So laser light have so very less bandwidth, so pure in color, Pure in color means what is the exactly color? If you will take so orange color laser. Orange color laser means exactly here 598 angstroms. Okay, so that spread is so just 598 to so 608. Here if you that means so total is 10 na? So total is 10 means so if you will come like this point, if you will come this point, so what is the value here means so exactly 598 plus 5. So 598 plus 5 means 602 angstroms here. So here 598 minus 5. Okay, so that means 593. That means here just 10 angstroms difference. 10 angstroms difference. In between 10 angstrom difference, that color of light doesn't change anything. That color of light doesn't change anything. So that's why we will say that here. So that is pure in color. Pure in color. Bandwidth also very less. The bandwidth of the laser beam is so very narrow. So while ordinary light spreads over the wide range, already it will discuss. So it will, so if you will take normal lights, not sodium light, if you will take any other ordinary light, so that wavelength spreading is nearly 100 angstroms, sorry, 1000 angstroms. 1000 angstroms. The bandwidth will be so more than 1000 angstroms also. More than 1000 angstroms also. But if you will take laser light, just 10 angstroms. Okay. Yeah. So the photons emitted in the stimulated emission have same frequency or wavelength. See here. So approximately so same frequency or same wavelength. So frequency and wavelength. So both terms are same here. Okay, so that means there is a relation between frequency and wavelength. That's why we can say that in terms of wavelength or frequency. Okay, so that's why here in case of stimulated emission, so that either wavelength or frequency have same, approximately same. Okay, now coming to the due to stimulated emission. Next point, due to stimulated emission, laser beam is single wavelength, that is the line width of the laser beam is extremely narrow. So whatever we discussed that only here. So here single wavelength, so single color is nothing but it will be single wavelength only. The width of the line is, so this width of the line also very narrow. And next one, the bandwidth of ordinary light is 1000 angstroms. In case of ordinary light, so it will be more than 1000 angstroms only. But in case of laser, so just 10 angstroms. Just it will be a 10 angstroms. Okay. Now coming to the narrow bandwidth of the laser light is called as high monochromaticity. Okay, so that means this narrow bandwidth gives is nothing but we said that it is a high monochromaticity. Okay, now so what is the definition of bandwidth is given? So the spread of the wavelength or frequency, okay, about the wavelength of maximum intensity bandwidth. Okay, so here from maximum intensity bandwidth, how much it's spreading. Okay, so here from here to here, total distance. From here to here, total distance is called as so bandwidth. What is the spreading of the wavelength or frequency? So that is the bandwidth here. Okay, so the spread of the wavelength about the wavelength of maximum intensity is bandwidth. The laser light is more monochromatic than that ordinary conventional light sources. Because of this monochromaticity, large energy can be concentrated into the extremely small bandwidth. Okay, because of this monochromaticity. What happened here? So large amount of energy is concentrated on a very small area. Large amount of energy is concentrated on a very small area. So because of this application, so because of this property, we can use this laser light in so many applications. Okay. Now we are discussing about the directionality. Okay, directionality. What is the directionality? Okay, the laser beam emits light only in one direction because of photons emitted in stimulated emitted process travels along the same direction or along the axis of the active medium. Okay, here so laser light is emitting So because of the stimulated emission. Okay, so in that stimulated emission process, all lights are moving in a same direction. All photons are moving in a same direction. Okay, that's why. So in case of laser light, so that light is traveling in a so particular direction, particular single direction. Okay, so that is the directionality here. Now it travels very long distances without divergence. Without divergence. Okay, so what is the divergence? Divergence means spreading. With increasing the distance, how much spread it will be. With increasing the distance, how much spread it will be. Okay, it travels along a distance without divergence. Okay, so without divergence, so it's travel more distance. Okay, see here, I am drawing here. So suppose one light is traveling like this. So laser light, if you will take another photon also there here. So with increasing the distance, so that spreading is very small. The spreading is, see here. So not much more, that spreading is very small. Okay, that spreading is very small here. So here is given, that graph is given here, see here. So with increasing the distance here, so the spreading is very less. Spreading is very less. This is the laser source here. So from source to here D1 distance. Yes. So from D1 source here, this is the source. So from source to D1 distance. So what is the angular, what is the radii, what is the radii of the this laser? Suppose if you will take a1 is the radii at a d1 distance, if you will take d2 distance, a2 is the radii of the this laser beam, radii of the laser beam. Now divergence formula, so divergence is equal to del theta. So del theta is equal to a2 minus a1, sorry, a1 minus a2 by d2 minus d1. So this is the formula for divergence. This is the formula for divergence. This del theta means, so simply we will call it as angular spread. So this divergence is nothing but angular spread. So angular spread is very less in case of lasers. Okay, because of this less without divergence. So that means approximately this divergence is negligible. Okay, so with increasing the distance, because your distance is so long, d2 minus d1 means, so here if you will take difference between very long distance also, so a1 minus a2 is very small. So a1 minus area, so area between, so here a2 minus a1, so a2 minus a1, so a2 minus a1 also very small here, very small here. So that's why, so compared to del theta is del theta value also very small. Approximately we can neglect the divergence in case of, we can neglect the divergence in case of lasers. In case of lasers, that means without divergence, it will travel long distance without divergence. And so laser communication is carried out on between the earth and moon. Okay, so if you want to communication between the, so earth and moon means, so we can use the lasers. So for satellite communications also, we will use the low intensity lasers, not high intensity lasers. We'll use the low intensity lasers for in communication process, okay. Now next one is the ordinary of the laser beam is expressed in terms of, yeah, so the directionality of laser beam is expressed in terms of divergence. If divergence is more means, so directionality is more, directionality is more. Okay, so if divergence is less means directionality is less. In case of lasers, so divergence is very less, so that's why directionality also very less. Okay, now coming to the, here example is given. So a1 is the radii at a point at a distance d1, a2 is the radii at a distance d2. Now divergence formula equal to del theta is equal to, so a2 minus a1 by d2 minus d1. Okay, this is the formula for divergence. Okay, now coming to the coherence. Okay, what is the time now? Yeah, so 7 minutes will be there. We will complete the coherence here. Here coherence. Yeah, two sources of light are said to be coherent if they have zero or constant phase difference between them. Okay, here we are taking two photons. So two photons are moving. Two photons are traveling. So in between two photons, photons. So what is the phase difference between them? If phase difference between them is zero or constant, if phase difference between them is zero or constant, so then we will call it as those two photons are coherent. Those two photons are coherent here. So see here, three light waves are traveling. Three light waves are traveling here. Those three light waves are same phase difference. Same phase difference. Okay, are so phase difference is zero or constant. Phase difference are zero or constant here. Okay, so at this situation we will call it as, so these are the coherent light. These light we will call it as coherent light. Okay, now coming to the, in case of normal light, that means sunlight. If you will take sunlight, so the light waves are travel like this. So different lights, this is not a monochromatic. Sunlight is not a monochromatic. Different colors will be there. Different colors will be there. So all combination of all colors will become a white light here. Okay, that's why here, so those all are having, don't have same frequency also. So different frequencies will be there. So they have different phases. Okay, that's why. So in case of ordinary light, ordinary sunlight, so the light will be spread like this, travel like this. Okay, the light will be travel like this. Okay, now if you will take single color means monochromatic light. So we said that LED is the example of monochromatic, one example of the monochromatic light. In case of LED, how it will be travel means, so they are monochromatic, that means same wavelength, they have same wavelength, but so they have not same phase. So phase difference is, so phase is different, phase is different. Okay, so not a coherent, so phase is different here, that's why these are not coherent. So do you know what is that wavelength definition? So wavelength definition, okay, so distance between the suppose wave is starting from here. Okay, so to complete the one wave starting here, suppose I will draw one line here. See here, I am drawing here. Okay, yeah, suppose this wave is traveling like this. Okay, so this wave starting here, and it will complete one oscillation and complete, so it will be complete another oscillation here. Okay, distance between these 2 points, distance between these 2 points here, we will call it as wavelength. Okay, otherwise here also we can take, so this is the wave here, so it will coming like this. So from here, so distance between these maximas, okay, these are the maximas here. So distance between the two maximas, distance between the two minimas is called as wavelength. Okay, so distance between the, so two maximas or distance between the two minimas is called as wavelength here. Okay, now so one color, so that means these are the not monochromatic, not monochromatic, sorry, these all are the chromatic, monochromatic, that means these all have same wavelength, all have same wavelength, but so they don't have same phase, they don't have same phase. Okay, in case of LED, but in case of laser, so they have, so monochromatic, so distance between two successive maximas are so constant. Okay, and so same phase, if you will take this point also, this point also, so there is a constant phase difference between, so these three waves here. Okay, so that is in case of lasers, okay, here there are two types of coherence all will be there. So one is the spatial coherence, and another one is the temporally coherent. So one is the spatial coherent, another one is the temporally coherent here. Okay, now coming to the, so what is the, so temporal coherence and what is the spatial coherence we will discuss. Okay, first of all, so temporal coherence, so the temporal coherence refer to the correlation between the light fields at different times at a point on the wave. Okay, we are taking here one particular point, so how much time, okay, here some, it will have some phase, Okay, suppose so yeah, here two waves will be there. So here two waves will be there. So at a P1 point, okay, P1 point. So how much long? How much long that? Yeah, wait one more minute here. Suppose here, so this phase difference between these two is 10. Okay, 10 radians. Phase difference between, so here one, this is the one wave, this is the another wave. So phase difference between these two is, so 10 radians. 10 radians. Okay, so if you will take after 10 minutes, after 10 minutes, after 10 minutes at the same point, at the same point, so phase, if you calculate the phase difference between these two, so that will be same 10 radians, same 10 radians after 10 minutes, after 10 minutes. So that phase difference will become 11 radians, 11 radians. Okay, so what is the time of here? Temporal coherence means, so up to 10 minutes, up to 10 minutes, these are temporally coherent. These two waves are temporally coherent. Understood? So that means, so if you will take at a particular point, if you will take at a particular point, so two waves are how much? So how much time they have, how much time they have, they will maintain a constant phase difference, constant phase difference. Suppose these two are maintained, so constant phase difference at 10 minutes, 10 minutes. Okay, so the temporal coherence is 10 minutes. Temporal coherence is 10 minutes, up to 10 minutes. So these are temporally coherent. These are temporally coherent. So after 10 minutes, what happened? So these phase difference will be changes. So this phase difference will be, suppose 11 radians. 11. So either suppose 20 radians. Okay. So again 10 minutes. So at that 20 radians. So 10 minutes. So they will constantly maintain 20 radians. 20 radians. How much time here? Okay, so if more time they will maintain the constant phase difference means, so that also very important one. Okay, if you maintain means, so constant phase difference, suppose if you maintaining 10 minutes means, in 10 minutes light will be, laser light will be traveling a so much distance, so much distance without any deviation, without any deviation. Okay, so that is about the temporally coherent. Okay, at a particular point, how much time, how much time they are maintaining a constant phase difference, that is called as temporal coherence. Okay, now temporal coherence refers to the fact that, yeah, what's the time? Yeah, so now we will complete the here, so then we will discuss about the, so temporal coherence tomorrow. Yeah, so now I will take the attendance here. If you have any doubts means you can ask, otherwise you can leave from the session. Okay, if you have any doubts you can ask, otherwise you can leave.